Yes, welcome everyone to today's SZ4D International webinar. I'm gratified to see so many people online, and the number is bumping up rapidly. Even in these challenging times, and with EGU looming, people are here for this. And that is no doubt a tribute to everyone's interest in Kelin's topic today, and in Kelin as a speaker, who we all know has often given us many really stimulating presentations. So it's my pleasure to introduce Dr. Kelin Wang from the Geological Survey of Canada, where he's a senior research scientist. Kelin is known to virtually all of you, I'm sure, as one of the leading researchers and thinkers, in a way, in the field of subduction zone geodynamics and the relationship from everything from earthquake hazards to much larger scale processes at subduction zones. Kelin, let's see, has a bachelor's degree from Peking University in China and a PhD in geophysics from University of Western Ontario. He's the recipient of the Tuzo Wilson Medal by Canadian Geophysical Union in 2015. He's been the Birch Lecturer at the AGU. I remember that lecture very well in 2015 also, and is a fellow of the AGU, as well as holds a position as a faculty and research professor, I think, at University of Victoria. So without further ado, let's turn it over to Kelin and listen to what he has to tell us about the cold Forearc Mantle Wedge.
Thank you, Harold and Emily, for the invitation and for the nice words about me. Yeah, hope I can live up to the expectation. Yeah, so let me minimize the, okay. Okay, so before I start, let me clarify, before I talk about 5 things, let me clarify 2 things. One is, how do I advance my slide? Yeah, I have some difficulty. Okay, yeah, I talk about, I clarify 2 things. First is many people contributed to the various studies reported in this talk. And these are students and colleagues, international colleagues, I wish to thank for their contribution. Second, I will cover a large range of materials today, and there's no time to explain technical details. So please bear with me in that regard. If you are interested in details, let's talk about it separately. Okay, the central subject of today's talk is this blue triangular area, the Forearc Mantle Wedge. I will, from 5 different perspectives, I'll talk about its thermal mechanical state and how it influences the megathrust slip behavior. Let's first start with briefly reviewing the thermal and petrologic state. I always claim the most fundamental aspect of subduction zone geodynamics, at least the shallower part, is this thermal contrast between the cold forearc and hot arc and back arc. Now we understand that contrast is because of a change along the plate interface. Below this depth, the plate interface is fully coupled. That means the mantle material travels with the slab at a full speed, inducing mantle wedge flow. That controls the thermal state of the arc and back arc area. In the forearc area, the thermal state, and for the same reason, and we have the megathrust basically has a down dip limit. And the shallow part of the megathrust can generate large earthquakes. And because of the mantle flow in the wedge here, the thermal state is pretty similar between different subduction zones to a large extent. But it can be quite different between subduction zones in the forearc, depending on the age and the thermal state of the incoming plate, as you all know. And the thermal difference between the incoming plate causes a large difference in the metamorphic dehydration processes of the slab. As we know, most of the fluid from slab comes up when the subducting crust changes from metabasalt to eclogite, basically from this blue to yellow area. And that transformation occurs at a pretty shallow depth for young slab, but much deeper depth for old slab. That causes a lot of difference. And dehydration also occurs in the subducting mantle, but its importance is not that obvious until much greater depths. To appreciate the difference between young and old slabs and warm, cold slabs in the dehydration, thermal and dehydration process, let's look at our most familiar end members of subduction zones. The young slab end member Cascadia and old slab end member Japan Trench. As I said, the dehydration of the crust, the change from basalt to eclogite, occurs at a fairly shallow depths for young slabs here, and for at a much deeper depths for old slabs here. As a result, most of the fluid is released at shallow depths to allow hydration of the Forearc Mantle Wedge corner in this area. So that corner is highly hydrated for young slabs. And for old slab, it's different. So when you see purple here, that means serpentine mineral is stable in this area, given the temperature and pressure condition. But it does not mean there must be serpentine. We need a fluid to produce serpentine, hydrous minerals. And for the cold slab, it is just not enough fluid here at this depth, but there's a lot of fluid being released at much greater depths to feed the volcanoes here. So that's the difference. And the degree of hydration is quite different between the two. Another important difference between young and old slabs is the seismogenic zone of the megathrust. For young slab, because of the thermal state and rheology, the seismogenic zone will terminate before it reaches the mantle wedge corner. For older slabs, the seismogenic zone usually goes beyond the mantle wedge corner. So these are important things I will revisit in the rest of my talk. So that's about all I have to say to review about the thermal state and petrology of subduction zones. And in this, you notice the mantle wedge flow here really controls the thermal state to a large extent. But I also notice in these thermal models, the Forearc Mantle Wedge does not participate in this flow. It is stagnant. And what's the evidence for the Forearc Mantle Wedge being stagnant, not participating in the mantle wedge flow? And there's different pieces of evidence, but the most direct evidence is what I'll talk about from my second subject. That's the stagnant kinematic state of the Forearc Mantle Wedge resolved from seismic anisotropy. As we all know, when shear wave travels through an anisotropic medium, it splits into two polarized components. And the particle vibration direction of the faster wave is called fast direction. It kind of represents material anisotropy. And the arrival time difference between the two waves kind of tells us the depth range of the anisotropy. And the shear wave splitting to determine anisotropy, the method has been applied, well, it was applied to a Cascadia a long time ago, and this is the work by Claire Curry and her colleagues. And at that time, using local earthquakes and shallow source and teleseismic event sources, they could tell that the shallow anisotropy, basically in the Forearc crust, is margin parallel. The fast direction is margin parallel, and the deeper anisotropy, and mainly in the mantle, and it's margin normal, very, very different. And we can tell the depth from the height, from the delay time, of course. And the interpretation for this difference between shallow and the deep is as follows. For the deeper anisotropy, margin normal anisotropy, and we understand what they explained, it reflects mantle flow, either in the mantle wedge return flow here, or in the flow below the incoming plate. As the mantle flows, the olivine minerals has a preferred orientation, and that preferred orientation gives rise to anisotropy. That's about the deep anisotropy. The shallow anisotropy, it was explained, and to reflect the crustal fabric as controlled by margin parallel compressive stress in the forearc. So that was explained, but what about the Forearc Mantle Wedge? And that was not resolved because they did not have enough stations, did not have enough earthquakes to resolve it. And to find more earthquakes and more stations, where do we go? And the most obvious place is Japan. And Japan Trench, after the 2011 Tohoku earthquake, they installed a very large seafloor cable system with numerous seismometers. And all these red squares you see on the screen, these are the seismometers that recorded the signal used in the present shear wave splitting study, and a lot of data. And also because they have so many earthquakes there, they could afford to throw away a lot of them and to use for this study only the events that are along the plate interface or in the upper plate. Therefore, whatever anisotropy we resolve, it is either in the upper plate crust or in the Forearc Mantle Wedge. Now we have a good opportunity to resolve the anisotropy of the Forearc Mantle Wedge. Without explaining details, here's the results. And from early studies, we know that from early studies using land stations, we know the deep anisotropy is just like Cascadia, and the fast direction is margin normal. And from the new study using the seafloor cabled seismometers, we know that the fast direction is margin parallel, again, similar to Cascadia, and in the same direction as the general directions of these active faults. And the interpretation of the contrasting anisotropies is also similar to Cascadia. Of course, the deep anisotropy, margin normal anisotropy, is due to mantle wedge flow here, similar to Cascadia. And the shallow one is interpreted to be to reflect the margin parallel rock fabric, as you saw from those active faults. So what about the Forearc Mantle Wedge here? And the result shows there is no anisotropy. The Forearc Mantle Wedge is isotropic, so that is evidence that it does not involve in the mantle wedge flow as the rest of the the mantle wedge. It also shows there's really no frozen-in anisotropy from any previous flow. And that seems to indicate the Forearc Mantle Wedge has always been stagnant. And that's quite important. And because it's stagnant, it becomes colder and colder with the incoming plate here. And without the mantle wedge flow to supply more heat, it becomes cold and can host hydrous minerals. And also because it's cold, its mechanical state is expected to be quite different from the rest of the mantle wedge. And that leads to our third topic. I'm going to explain the Forearc Mantle Wedge corner is pretty stiff. And we know this from by observing geodetic post-seismic deformation after large subduction earthquakes. In studying post-seismic deformation after large megathrust earthquakes, and we use a model that includes elastic upper plate and downwind plate. And the model, the important part of the model is the viscoelastic mantle. And what about the Forearc wedge? The Forearc Mantle Wedge, for the time scale of earthquake cycles, like a few hundred years, 1,000 years, and it's considered to be elastic. Therefore, we use elastic cold nose and to represent this behavior. Now, let's look at the two-dimensional model of subduction earthquake post-seismic deformation, including this elastic cold nose here. In this model, we assume the cold seismic slip occurs like that along this part of the megathrust and induces cold seismic deformation. But what is shown here is post-seismic deformation 5 years after the earthquake. And this is the displacement field here in arrows in cross-section view. And what's important is the what we observe at the surface. In the horizontal direction, this dashed line, we see the famous opposing motion, the rupture area moving landward, the rest of the area moving seaward, opposing motion. But the most important for today's subject is the vertical deformation in this area. It's the uplift around the landward edge of the cold nose. And if we do not have our elastic cold nose here, and our model will not produce uplift here. But you can say, well, that model produced too much horizontal motion here, too fast. That's no problem. If we increase the mantle wedge viscosity here, we can reduce the horizontal motion, but still we do not see the uplift. Why do we see uplift here in the presence of the Forearc cold nose? And if you look at this little area, we see the reason. As the earthquake induces a stress change, and the viscoelastic relaxation of stress change induces a mantle wedge flow in that direction. And that flow is very different from the background mantle wedge flow I mentioned earlier. And this is just a perturbation on whatever background field. In that perturbation, and if the mantle flow, if it encounters a stiff cold nose here, and the flow is deflected to flow a little bit upward to cause uplift here. If there's no cold nose to deflect the flow, and the deformation will simply goes horizontally in the seaward direction. So that explains why we have this diagnostic uplift to tell us there is a cold nose here. Having understood the mechanism, let's look at some real earthquakes. Of course, we go back to Japan first, and after the Japan earthquake in 2011 was recorded by many geodetic stations, GPS stations. And what's shown here is the post-seismic deformation 5 years after that earthquake, again recorded by so many stations. And because I'm used to looking at subduction going from left to right, let's flip it here. And the most important is the vertical deformation here, and especially vertical deformation, the uplift in this area near the volcanic arc here. And that is evidence for the uplift, post-seismic uplift in the presence of the cold nose. And our model, three-dimensional model, and can explain this very well. You can see the green arrows here. And the model is similar to the 2D model I just showed, but except it's 3D. If you look at the profile here, we can see, and the model fits the data quite well. And we have looked around the world to see if there's evidence for this. We actually have not seen any places that does not have this behavior. And the problem is most of places do not have enough data. They certainly have data consistent with this uplift, but it's not enough to constrain a model. And but in a few places, we do have enough data and to allow the development a pole-size deformation model, including Tohoku. And depending on the site of the earthquakes, in some places the uplift is larger, some is smaller, but they have also a consistent pattern. The most remarkable is this event, the largest megathrust earthquake or any earthquake ever recorded on Earth. Of course, back in 1960, and these data were not geodetic observations, not GPS. And these are geological observations 8 years after the earthquake collected by George Plafker. And these purple dots show the site, George Plafker's field sites for these observations. And the most intriguing is in this area. Again, near the volcanic arc, it shows up to a meter uplift. At that time, that was interpreted to be coseismic uplift. And because there was no such concept as pole-seismic deformation in those early days. However, even with the most recent rupture model that has a lot of rupture here, and we simply cannot produce uplift here, coseismic uplift. In fact, we produce a bit of coseismic subsidence. And any no reasonable models, coseismic rupture models, can ever produce uplift here, and so far from the rupture zone. So that uplift has remained a mystery for the past 50 years. Now the mystery has been resolved. Now we understand it is simply pole-seismic uplift due to viscoelastic stress relaxation in the presence of the cold Forearc Mantle Wedge. And it is quite remarkable. And because George Plafker's data set, these observations, these are transforming observations, and they are a milestone in our understanding of plate tectonics and megathrust earthquakes. It just humbles me to see that 50 years later, we are still learning from this data set, new things. Okay, so now let's continue with the megathrust behavior. And now let's talk about what happens around the Mantle Wedge corner along the megathrust. Let's first revisit the thermal contrast between warm and cold slab subduction zones. And as we recall, for warm slabs, because of the shallow dehydration, mostly because of the crustal dehydration, and the Mantle Wedge corner is highly hydrated, and for a cold slab is less hydrated. And another difference is for warm slabs, the megathrust seismogenic zone terminates at pretty shallow depths before reaching the Mantle Wedge corner. So this is important again for this subject. The hydration. This is a global compilation based on mineral calculations of global subduction zones, the hydration state of the Mantle Wedge corner. And the color represents the degree of hydration. If you see red, it's highly hydrated. If you see blue, there's not a lot of hydration here. And the three places that are red, they happen to be the places where we have the most abundant observations of episodic tremor and slip around the Mantle Wedge corner, what we call ETS or similar behavior. Here, but the problem is, given the high temperature, warm temperature of these warm slab subduction zones, this is Cascadia, and this area of the megathrust is supposed to behave viscously and to exhibit viscous shear instead of frictional behavior. But ETS reflects some mild frictional instability. So how do we have a frictional behavior reflected by ETS and in the zone of a viscous shear? So that becomes quite interesting. We have to come up with some geological explanation. And here's the explanation. And because of the very high degree of serpentinization, and this little corner, and which does not have a large area, it probably will be fully saturated. It doesn't take a long time, and to reduce permeability. And the flow of fluid will deposit a large amount of silica at the base of the upper crust that also decreases permeability. As a result, we have a zone of very high porphyry pressure. When the porphyry pressure is high enough, it'll dramatically reduce the frictional strength of the fault and to be lower than viscous strength. Therefore, it produces a localized zone of friction here, and between a zone of viscous or semi-frictional behavior. And so that provides the geological condition for ETS. But another condition for this to happen is the seismogenic zone has to terminate before reaching the mantle wedge corner. And that condition is met in all our 3 warm slab subduction zones here. For colder slab subduction zones, the megathrust seismogenic zone goes beyond the mantle wedge corner, and ETS does not happen around mantle wedge corner. Of course, other type of slow slip events and tremor and VLFEs will occur in other parts of the system. Okay, so talking about the colder slab subduction zones and seismogenic zone going beyond the mantle wedge corner, and we can continue with this subject and to talk about the 5th topic. That is how serpentinite affects the deeper part of the megathrust to affect its seismic behavior. And for this topic, let's use the example of the 2010 Maui earthquake shown here. And shown here is the rupture distribution, slip distribution of that earthquake. As you can see, the slip extended to at least 50 kilometers. And it's probably is much deeper than the Moho, than the mantle wedge corner. And however, from the stress drop distribution derived from the same slip distribution, we can see most of the stress drop on the megathrust occurred shallower than 40 kilometers. And deeper than 40 kilometers is stress increase and during the earthquake. So it actually to resist rupture, it slipped passively and producing stress increase. And also shown here are aftershocks. And if you look at the cross section here, and we see the aftershock distribution has an interesting feature. That is around the mantle wedge corner and deeper, there is a gap in interplate aftershock distribution. And so all these things we think are related to the mantle wedge serpentinization. And why is that the case, and this is the reason. And we think serpentinization occurs along the base of mantle wedge. It's unlike warm subduction zones. It's a lot of serpentinization, but there's limited serpentinization, but still occurs, but mostly along the base of the mantle wedge. And the second is we think serpentinite is entrained into the megathrust to affect its frictional behavior. So these are the 2 reasons. And therefore, we need to look at what kind of serpentin minerals are produced in this process along the base of megathrust, base of the mantle wedge. And here's what happens. And based on predictions from geological studies of the serpentin minerals in this environment. And what's shown here is the temperature along the megathrust. That is the base of the mantle wedge here. If you go deeper. And also same from this model. And also temperature predictions if you use a different friction coefficients. And we can see as we go deeper into the subduction zone here and warmer, and the serpentine minerals and will be produced. Different serpentine minerals will be produced along the base of mantle wedge. It start with lizardite chrysotile, and through this transition here, with either of these two reactions, eventually it'll turn into a completely antigerite. And this transition is a mixture between lizardite chrysotile and antigerite. And so we have this change in the type of serpentine minerals. And this change becomes important to our frictional behavior. Behavior. And again, we expect the most of the serpentine minerals is lizardite chrysotile at the shallower part of the base of mantle wedge. As we go deeper, and becomes completely antigerite. And these serpentines will be incorporated, will be entrained into the megathrust zone, fault zone, to have these patches of serpentine rich patches. There are numerous studies of serpentine friction under hydrothermal conditions. And I will have no time to review these studies, but in summary, all these studies show that lizardite and chrysotile, they show stable sliding under any condition. But antigerite is different. If the temperature is high enough, and it may exhibit some unstable slip, that means it may produce earthquakes. So that can explain what we see here, the gap, the aftershock gap here. So that's our hypothesis, and we expect the down dip of the mantle wedge corner, the megathrust zone is predominantly velocity strengthening, but it can allow rupture propagation, and such as in the 2010 Maui earthquake. And that propagation is passive, it's driven by the shallow part. Therefore, it has some stress increase instead of stress drop. And around the mantle wedge corner, we have lizardite and chrysotile entrained from the overlying mantle wedge, base of mantle wedge. And because they are aseismic behavior, they cause a aftershock gap. They do not produce aftershocks here, even though we have afterslip. And further down dip, and we have mostly antigerite, and these antigerite patches in the fault zone may be responsible for the generation of aftershocks. Now I have gone through all my 5 things, and I welcome any questions. Thank you.
Great, thank you very much, Kelin. I'm sure that I'm speaking for everyone when I clap there, or clapping for everyone. Folks who have questions, please type something into the chat window and I will read them out, or if necessary, call on you. And while people are preparing a few questions in the chat window, I can just say one preview is that the SZ4D International webinar will now take a pause for December. There's lots of things going on in our world, of course, with AGU and holidays coming, and we'll be back in January and February with some new webinars to come. So stay tuned for that. While we see who's adding some questions, and please, folks, feel free to do so. Maybe I'll start out with a question. As we think about the geometries of the relationship between the seismogenic zone and the mantle wedge corner for cold versus hot and everything else, what implications do you think those differences may have for the loading of the seismogenic zone, I guess, and the relationship to stress changes that may launch megathrust events?
Well, if the seismic zone is wider in the down direction, and the lock zone is also supposed to be expected to be wider, right? And I think that's what you mean, right? Loading is interseismic loading.
Yeah.
It should be wider, and that certainly will affect the interseismic deformation. Maybe modulate stress changes in different ways.
All right.
Did I answer your question?
I think so. Of course, there's lots to talk about. Roland Bergman has a question. You also worked on interseismic models, including viscoelastic rheology. Does the cold, stiff nose affect secular interseismic velocity fields and models?
Secular velocity, geodetic velocity, right? Yeah, well, I think that's what you mean, right? Like interseismic deformation or long-term deformation.
Roland, you can go ahead and clarify.
Roland, hi, Roland.
Hi, Kelin. That was really a great talk. I did mean interseismic velocities late in the earthquake cycle and how we use those to invert for coupling distributions. And you have worked on that. So I was wondering if that additional complication of the rheology structure also affects those kind of inversions.
Yeah, I asked question. I asked the clarify. I gave this talk before. Some people asked me about the long-term impact of this the behavior. For the long term, it can deform, right? It can deform in different ways. But over earthquake cycles, and because of its low temperature, it should be, for that time scale, it should stay elastic. Actually, when we first observed ETS, it was kind of surprised because I thought at that time that the mantle should be have viscous behavior, but apparently it was cold enough to be elastic, to accumulate enough elastic strain energy to be released episodically in ETS events. So it is elastic. So I think that answers your question.
Yeah, thank you. That was great.
Thank you. Okay, Will Struble has a question saying, fantastic talk and thanks so much. He's curious, given what you have presented here, if you have any thoughts on the effects of the mantle wedge and mantle flow on long-term topography generation in Cascadia, both in the coast ranges as well as, Puget Lowlands, Willamette Valley, et cetera.
Yeah, that's a very good, good question. But it can be complicated. I think you're mostly thinking about the effect of the mantle wedge on topography, especially when you have hydrous minerals. Hydrous minerals, when they form, they expand, right? They reduce density. But globally, we really do not see a high topography right above the Forearc Mantle Wedge. I guess the reason is as we form the hydrous minerals in the Forearc Wedge, and the hydrous minerals is also removed from below and get entrained into the megathrust. And to an extent, we do not really see a high topography there. And it is intriguing. It's a very good point, but just because we haven't seen consistently high topography due to this effect, we think the hydrous minerals are being removed from below. And for the rest of the mantle wedge, well, just because of the hot state, the whole thing tends to be a lighter, lower density, and it tends to be higher. So that's a small effect on topography. I hope I answered your question. Thank you.
As a follow-up, you showed the post-seismic uplift in the expected location. Do you think that contributes to a permanent signature, or is that a cycle
that's also a good question. As far as we can tell, eventually the deformation will reverse direction. And so later in the interseismic period, that area will experience some subsidence. As a result, the net effect over the entire earthquake cycle is no net accumulation of topography.
Great, thank you. Emily's question is next. is there any chance that the mantle wedge is soft enough, even though stiff generally, to prevent elastic energy buildup in the ETS zone and thus provide an alternative explanation of the slow nature of these events?
Yeah, that's interesting thought. But let's say two aspects from the prediction of rheology. Yeah, for warm subduction zones, yeah, and for that, yeah, for that kind of material, if you have mostly mantle material, and at that temperature, like below something like 700, 600, 700 degrees, and it's supposed to be pretty hard. It's a brittle behavior, elastic. So that's from rock rheology perspective. And observationally, if we do see ETS, episodic slip, that means energy, elastic strain energy is indeed stored there in some way, right? And of course, under some conditions, I think the question is why it does have energy, why the slip is slow, right? And it's slow not at seismic velocity. My view is mostly the fault behavior, and that's really not addressed in this model. And how it's really not the seismic slip, but it released strain energy more slowly as other slow slip events. That's the mostly fault behavior, frictional behavior.
Okay, let's see. Ansoke, what about fluids in cold subduction zones? Do you think that any part of it is trapped within the subduction channel and may contribute to coupling changes in those settings?
Yeah, there's certainly a lot of fluids coming out of cold slabs, and they come out of cold slabs at all different depths. And the difference from warm slab is just a peak dehydration, and due to the transformation of basalt to eclogite, and that happens deeper. And but certainly there's the fluid comes up and it'll cause some salinization along the base of the mantle wedge, and also certainly there should be fluid in the megathrust for sure. Yeah, this is just out of question. There should be. I don't know how much. I'm not a believer of a lithostatic fluid pressure for the entire megathrust, but I think there's certainly a high, pretty high pore fluid pressure. Maybe not as high as the mantle wedge corner for the warm slab subduction zones. But there's certainly, that's quite true. There's should be quite some fluid and causing some elevated fluid pressure.
Great, yeah. Oh, questions keep rolling in and we have some time, so I'll keep going. Art Frankel asks, the uplift of the 1960 Chile earthquake is very close to the volcanoes. Could the uplift be affected by weakness in the crust in the volcanic areas?
Yeah, and you're saying the deformation, could the deformation be due to deformation of the upper plate? That's always in the thought of a lot of researchers, I understand. But as far as I can recall, there's really not a lot of evidence for it, or any evidence for it. If there's anything, the earthquake produces extension co-seismically there, and it should not produce like a thrusting motion to cause uplift. And it would be pretty complicated to explain it that way. And explaining this as the effect of post-seismic deformation, and it's very simple. That's another reason I prefer this kind of explanation.
I'll take things slightly out of order because this is sort of a follow-up from Alice Agnes Gabriel. Could there be a co-seismic contribution to Plafker's measurements of uplift? Co-seismic.
Yeah, I would say no. Yeah, there were efforts. Notice what I said, that no reasonable co-seismic slip models can produce that substance. But you can if you try very hard. And how do you produce it? You have to introduce a slip at large depths. That indeed happened in some of the previous models. People just didn't talk about it. But if you look at the paper, the pictures, figures, they are there. And if you have a large cosine slip, and from 70 to 100 kilometers depth along the megathrust, you can have some uplift, cosine uplift for sure. But as far as we understand today, and that just simply not reasonable, right? For that depth, and we cannot have seismic behavior along the megathrust. And I don't even believe we can have after slip per se. We can have some shear deformation, like the flow of shear zone, but not like a shallow after slip. It's just the fault. It's just not there to behave that way.
Thank you. Madison Bombardier asks, is it possible that the ETS could originate from the interface between the cold Forearc mantle and the continental crust? Or on the other hand, between the cold Forearc mantle and the subducting plate? Or is it only possible for ETS to originate from the interface of the subducting and continental plates at the uptick corner of the wedge?
Yeah, I'm aware of this. There are different, well, there's still different views of where the tremor, especially tremor. Well, I guess there's a little question. The slip is has to be along some fault, right? It's most likely along the megathrust. And the tremor is a good question, but from the studies of high accuracy tremor location, if you call it tremor location, like the location of low frequency earthquakes and very low frequency earthquakes embedded in tremor, and seems like if they represent tremor, and seems like tremor has to be along the megathrust. The megathrust does not have to be a single contact. It could be a zone of, I don't know how many, like 500 meters thickness, some thickness. And well, but the possibility of having tremor above the megathrust, and it is there, certainly cannot be excluded, but I think most of the high resolution studies point at tremor in this kind of event occurring along the interface.
Great. Brandon Shuck, what is the behavior of the mantle wedge in subduction zones where there is significant lateral migration and rollback, e.g. the Hellenic Trench? Will the cold wedge eventually heat up and change from stagnant to mobile state?
Yeah, that's a very good question. Well, it really, I honestly, I haven't thought about it. It's a good question. It's from my future research agenda. But let me just have some immediate response. My immediate response is when you have rollback, the whole system follows. So the configuration for that, the rollback does not mean you open a window, right? The whole system follows, like the trench will go that way and the upper plate of Forearc will go that way. So the configuration does not change a lot. So I think in that case, and what I described still holds, right? But just it may move around in the bigger mental system. But if the trench does not move, but the slab becomes steeper or shallower, certainly that'll change things, right? If for some reason I can see how likely that can be, and for the shallow part of the slab, for some reason slab becomes a lot steeper, and the trench position does not change. And certainly you open up some space, and you expect hot material to fill it, and that can cause changes. But I don't know how likely that can be. Yeah.
Interesting one. Yeah. Amir Abul Hassem asks for the
Another earthquake?
Preview of earthquake early warning from California, but don't worry, it's small. Amir asks, for the dimensions and rates of the post-seismic uplift due to the cold nose, can you mention some typical numbers, at least for one type of slab or age?
Oh, it also kind of depends on the time after the earthquake, right? And if you look at Chile, that 1 meter uplift, that's cumulative uplift, and that's observed 8 years after the earthquake, and that's a huge earthquake. And for Tohoku, it's I think it's on the order of like 50 centimeters or something. That's 5 years after. That's also a very large earthquake. So yeah, that's on that order. But typically for other earthquakes, for Maui and other places, it's maybe the 20 centimeters and on that order. Yeah.
Okay, great. David Chapman, around slide 28 to 30, discussing the ETS, your isotherms show no drawdown from subduction. Are we just too shallow to show the regular drawdown effect?
That's correct. Yeah. You're an expert in this. Yeah, certainly. Yeah. It's if it's colder, for colder slab, there is certainly a drawdown. You have a cold core in the slab for sure. Yeah.
Okay. And Wai Liu asks, do you think the effects of cold noses should be considered in the general simulation of post-earthquake deformation, especially when we just use the GPS data in the back arc?
The answer is yes. Yeah, we have started doing that in the early models we produced when Yan Hu was here as a PhD student, and those models did not have a cold nose. We did not quite appreciate the importance of cold nose. But they still work for large scale deformation. But for a shorter term post-seismic deformation, and like when we get closer to the area, and we do need a cold nose. So in our recent post-seismic deformation models, we always include cold nose.
Great.
But well, the difference is that if you only look at the very long-term intraseismic deformation, like for Cascadia, and 300 years after previous earthquake. And in that case, and with or without the cold nose, makes very little difference.
That is the last one that's been entered here. Anybody who wants to get a last question in is welcome. We have a minute or two, otherwise. All right. Well, I think that I can speak on behalf of all the more than 200 people who are online today participating, that it's been an excellent presentation and really very interesting. Fabulous talk, great Q&A session as well. Lots of great questions came in. This presentation is recorded and will be available at the SZ4D.org website within a few days. We usually get them posted by Monday or so. People can review it if they like to. Thanks very much, Kelin, one more time on behalf of SZ4D and everyone else for a really wonderful talk. We appreciate it so much.
Thank you. And thank you all for listening to me.